So I'll be talking about the quantum annealing for automated feature selection in stress detection. So the concept of stress detection consists of taking information from various physiological parameters. So researchers have used different physiological parameters like ECG, respiration, body, postures, and etc. So these combinations usually increases the accuracy of stress detection. However, certain physiological parameters might perform better than others during certain tasks. So optimizing the number of predictors during the training phase is important to reduce the complexity of the deployed model. Also, optimizing the number of predictors under limited training data sizes could be useful analysis for reducing training costs. So this some background on quantum annealing. So it's a basically heuristic search algorithm for finding the global optimum. So it takes advantage of quantum tunneling to escape local minimum to head towards the global optimum. So it is usually always guaranteed to converge to the optimal solution. So in our work, we have used the D-Waves quantum processing unit for implementing the quantum annealing algorithms. So the Davis quantum processing units is basically a collection of qubits which are arranged in graph structures. So the optimization routine is usually offloaded to the QPU, and the qubits and the couplets are initialized as the biases and biases and weight, and then the solution is the lowest energy configuration that is returned. So the contribution of this work is that first of all, we have proposed a hybrid classical quantum machine learning pipeline for automated feature selection, and this is applied for selecting the optimum subset of features from some physiological signals with particular application to detecting stress in automobile drivers. And then this technique is compared to typically adopted methods for feature selection in classical site like p-value, mutual information, etc. So for stress, the signals that you are considering in this work are the electrodermal activity collected from the hand and foot, and the respiration and the ECG from the chest. Then features are extracted from these four signal streams, and then Pearson correlation coefficient is calculated between the feature and the target variable. So the bias matrix is basically the feature target correlation coefficient, and the weight matrix is the feature correlation coefficient. And then basically we are sampling a click using the D-Waves click solver, and the hypothesis is that the click with the lowest energy configuration should be the solution. So this is the overview of the architecture. So basically the signals are pre-processed, features are extracted, and then the data is split into training and test set. So then the training data, from the training data, we calculate the feature correlation metrics and the feature target correlation metrics, and only these metrics are then offloaded to the quantum subroutine. So then these are used to initialize the bias, initialize the bias and the weight. There is the qubits and the couplets connecting the qubits. And then after the annealing, the clicks are sampled from the binary quadratic model, and the solution at the lowest energy is selected. So those features that are selected, those features are then selected from the training data to train the model, and then also to test the model. So random forest classifier is used for this purpose for training and testing. So that the data set that we have used in this work is a online available drivers data set. So basically it starts with the data set, the driver drives through a series of city, highway, and rest period. So these 7 records are selected for analysis, and first of all the signals are normalized in the range of 0, 1, and then Butterworth filter is applied to filter the ETA signal, the respiration signal, and the ECG signal, and the components higher than 1 Hz for ETA is cut off, 10 Hz for respiration, and 40 Hz of ECG is obtained. So in total 12 features are extracted, 6 features are extracted each from the hand EDA and the foot EDA, 6 features from respiration signals are extracted, and 21 features from ECG signal is extracted. So for analysis, we'll be doing 2 types of analysis. One is the qualitative evaluation, one is the quantitative evaluation, and also this will be doing under different training cycles. Okay. So for the quantitative evaluation, our objective is to see the consistency of the features that are selected when we reduce the number of training set. So for example, if we use 100% of the training set, or 30%, 20%, and 10%. And for the quantitative evaluation, we'll see that those features that are selected, what is the F1 score that we get for classifying the particular feature sample as low, medium, or high stress. So this is the qualitative evaluation that we have obtained. So if you see that these stacked bar diagrams represent the percentage of selected features from each signal strings. The red represents those selected from ECG, the blue from respiration, violet from respiration, the sky from foot ED, and the green from hand ED. So for quantum, and we compared it with mutual information, p-value, and the Pearson correlation. So if you see that if we use quantum annealing, if we reduce the number of training set from 100% to 30%, we are getting more or less consistent features. And also, like if we further reduce to 20% and 10%, we don't see much inconsistency in the selected features. Whereas in other cases, for example, in mutual information, if we use 100% of the training feature, we get all the features from ECG signal. But if we reduce it to 30%, we get all the features from all the four signal streams. Okay, and this is also not consistent as we reduce the training set. Similarly, this is seen for Pearson correlation and also for p-value. And if we go ahead to the quantitative evaluation, so this shows the average F1 score that you have obtained for the three classes of stress: the high stress, medium stress, and the low stress. So in case of quantum annealing, we see that if we reduce, if we use all the training data that is represented the blue bar, and all the 30% is represented with the yellow, the green represents 20% training data, and red represents 10% training data. We see that more or less we are getting a more or less the F1 score is constant, and not much significant difference is there between the F1 scores that is obtained when it reduce the training sizes. So this also can be seen as the if we see the trend line is more or less constant for all the three classes. But for mutual information and p-value, we see a clearly decreasing trend. So as you reduce the number of training data, the F1 score also drops significantly. The one exception is the Pearson correlation, but overall the Pearson correlation did not perform well because it did not compared to the other methods. So in this way, you can see that quantum annealing has been consistent in both qualitative and in quantitative way for this particular application in stress detection. So in conclusion, we have proposed novel method for automated feature selection using quantum annealing. So the features are selected by sampling the lowest click from the D waves QQ, and this has been compared to typically adopted methods for feature selections. This is the Pearson correlation, p-value, and the mutual information. So you can see that the quantum annealing has performed comparably with the classical techniques. However, if we reduce the training data, we see a slight advantage if we use quantum annealing, both in terms of it returns consistent set of features and also consistent F1 scores. So it will be an interesting direction in the future to see if this particular method can be applicable for other diverse problems and large-scale problems where feature selection is an important optimization step. So, any questions? Thank you.
Oh, thank you, Rajiv. Again, any questions, please add them to the chat. I was curious if the limitations of the hardware, especially in terms of the size, you think may actually be significant for adding new features or representing the current features.
Yes, so you mean that if we have a number of features, more number of features that the current D-Wave system can currently support, the number of variables?
That's right.
Yeah, so yeah, this can be a problem where one method could be like if we use a bootstrapping technique, so that like we select like samples of features from the overall, and then like use those samples, so that subset of those features to and then feed it to the D-Waves quantum processing unit to solve this problem. But as the scale of the D-Waves Q-cube increases, like as it can accommodate more qubits, I guess we can accommodate more problems where the variables are larger in number.
But the bootstrapping procedure may be the solution in the near term. That sounds interesting.
Yes. Yeah.
Okay. Well, Rajiv, thank you very much.